Okay, good morning, good afternoon, good evening, everyone. Thank you for joining today's webinar on advancing sustainability with materials, membranes, and electrochemistry. My name is Xin Xie at Georgia Tech. So I will be the moderator today. So let's get started. Okay, so so this is today's agenda. Again, my name is Xin Xie. And then basically I would do a very short introduction and there's just some housekeeping stuffs. And then we will have two presentations, each about 25 to 30 minutes. And then we will have a Q&A session together after the two presentations. And then we will do some closing remarks. Okay, so just before we get started from the webinars, just something to let you know. So first of all, this webinar will be recorded and then made available on the IWA platform. And the second thing is the speakers are responsible for secure copyright permissions for any work if they are present, if they don't have the equal copyright holder. And the last thing is that opinions, hypotheses, conclusions, and recommendations contained in the presentations and other materials are the sole responsibility of the speakers and do not necessarily reflect IWA opinion. And for the audience, so feel free to use the chat to do some general interactive activities. And then, but if you have questions during the presentation, please use the Q&A box. Okay, so we will get back to these questions after the two presentations. For the audience who are still not an IWA member, so welcome to join IWA. So you can either scan the QR code here or go to the IWA website. And then you can also use the code here, okay, so to get a 20% discount off for the new membership. Okay, so because this webinar is also hosted by our Nano and Water specialty group, so I just want to say just a very brief introduction about our specialty group. So we have a Nano and Water specialist group provides an active forum for the professionals interested in application or implication of nanotechnology. And then what we are doing here, we aim to promote research in environmental fate transport and risk of nanomaterials. We also provide a platform for exchange knowledge. We also stimulate the development of nanotechnology from lab scale to technological scale for drinking water and wastewater applications with less risk. And last one, we also try to extend the knowledge to other fields and applications as well. So for the new members, when you apply to the IWA membership, you have the opportunity to pick the specialist groups, and then welcome to join our Nano and Water specialty group. Okay. Okay, so with that, I would like to introduce the two speakers today. So the first speaker is Dr. Apita Idia, and she's currently a postdoc at Rice University, working with Professor Manny Malek. And then she earned her PhD in environmental engineering with a minor in chemical engineering at the University of California, Los Angeles in 2022. Her research delves into the influence of membrane properties on interfacial phenomena and the membrane-water interface, as well as the interactions within membrane structures. She also holds an MS degree in chemical engineering from Carnegie Mellon University, and then Bachelor of Technology degree in chemical engineering as well from the Visvesvaraya Technological University in India. And also our second speaker, Dr. Yimin Liu, very similar career path. He's also a postdoc. He's a Rice Academy postdoc in working with Professor Qilin Li. And then he also received his PhD from UCLA. And in addition to that, he also got his MS degree from UCLA under the supervision of Professor Stevie Jaspi and Eric Hook. He got his bachelor's degree from Tsinghua University in Environmental Engineering in 2018. Overarching goal of his research is to facilitate the circularity of water and critical minerals. Specifically, he develops platform treatment processes by exploring electrochemistry, membranes, advanced materials, with a focus on solid water interface. He has published first author research articles in journals such as in Nature Communication, Environmental Science Technology, Water Research, and Journal Membrane Science. Okay, so with that, let's welcome our first speaker, Dr. Apita Ide. So please let me give you the control.
And thank you so much for the introduction, Professor Shah. Hi, everyone. My name is Arpita Itya. I'm a postdoctoral research associate at Rice University. And today I'm going to be talking about one of my research projects that I worked on as a grad student at UCLA on leveraging materials chemistry, membranes, and electrochemistry for sustainability. So start with a broad introduction. Climate change and waste generation stand as the defining challenges of our era. And without drastic action, we only expect climate change to worsen and urbanization and overpopulation to outpace waste reduction. As governments across the world implement ambitious targets to curb the anthropogenic impacts of climate change, the concept of circular economy has garnered interest, specifically at the food, water, and energy nexus. The water sector is uniquely poised for this transition due to its intrinsic circularity and the environmental, economic, and social value of capturing the resources that it handles. The water sector handles an array of resources predominantly found in wastewater that are valuable and critical, bestowing opportunities for revenue generation and diversification. For instance, at the water energy nexus, we have critical metals and elements that are found in industrial and other kinds of brines and wastewaters that can be recovered to help complete the cycle on the circular economy of green energy economy. And at the food water and nexus, we have nutrients that are present in food and agricultural wastewater that can be used, that can be then recovered and reused. So with that, it brings me to my first project that I worked on as a grad student at UCLA at the food and water nexus. So food and agricultural wastewater is rich in a lot of nutrients, specifically nitrogen, potassium, and phosphate. Recovery of these nutrients is essential, and specifically for phosphate, that is achieved through struvite precipitation. Struvite is, however, dependent on soil pH, can have a high magnesium content that is not always beneficial to plants, and can have heavy metal contamination, which is deleterious to plants. So with this project, what we wanted to do was to see if we can recover phosphate using membranes. At the time that we were working on this project, there were very few membrane technologies that existed that were highly selective for specific particular ion species. Transport across membranes was governed by one of two main mechanisms, one of them being size exclusion, where smaller particles are allowed to pass through the membrane and larger particles are sieved on the surface. The other mechanism was charge exclusion, where charges which have the same moiety as that of the membrane were rejected, whereas unlike charges were allowed to transport and hop across. So what we wanted to do was develop a membrane that can differentiate between ions of similar size and charge. So for this, we look to facilitated transport membranes. And these are essentially polymeric membranes, or some in cases non-polymeric as well. But however, membranes that can facilitate the transport of specific target molecules across it. And for this, they use extractants, which are added inside the membrane matrix, and these act as selective entities. These bind with the target molecules to form complexes, and then either the complex is transported across or the ion itself is transported across by hopping across from one site to the other. So it would be something similar to adsorption on one side, moving across, and then desorption on the other side. But crucially, this is not an adsorptive membrane. So adsorptive membranes, as the name suggests, end up absorbing the specific target compound. And as a result, they become saturated and require drastic pH changes to desorb the target ion. This can also result in losing efficiency over multiple cycles. And this makes the process inherently not continuous because we have to stop it to be able to regenerate the membrane. So what this tells us is the choice of extractant that we have inside the membrane is extremely crucial. It must be selective for the target ion. However, the complex formation should be easily reversible without excessive pH changes or any other drastic changes to be able to recover the target ion. So what we did in developing our membrane was look towards coordination chemistry. And we found that many transition metals exhibit preferential absorption selectivity towards phosphate. For example, iron can form inner sphere, something called as an inner sphere complex. These are strong covalent complexes where phosphate absorbs onto the surface of the transition metal oxide. However, this would be something along the lines of adsorption or an adsorptive membrane if we use inner sphere complex metals. And this would lead to high pH changes being needed to be able to regenerate the membrane. The other kind of complexes that some transition metals can form are called outer sphere complexes. These are specific in the sense that they have covalent characteristics. However, no new bonds are formed, and predominantly the electrostatic forces are dominant within these membranes. So in this entire project, we had three main challenges. One was to develop a membrane that is selective for phosphate transport. We have to understand the specific ion transport dynamics and try to improve the performance metrics. So for the first step, we chose to develop a membrane that was selective for phosphate, and the choice of the extractant for this membrane is the most important step here. So we found through literature research that high-risk manganese oxides are known to form outer sphere complexes in phosphate in free solutions. So we wanted to see if these will maintain the same properties inside a polymeric matrix as well. So what we used was the principle of a mixed matrix membrane, where we used these HMOs as dopants. To improve the selectivity of the membrane itself, we use a cation exchange membrane. This way, it would reject all anions. So using a cation exchange membrane allowed the counter ions to diffuse across without any issues. And the hydrous manganese oxides present inside the membrane would allow for a selective path for phosphate to hop across. Whereas all the other ions in solution that do not form any specific complex with the HMO will be rejected by the background cation exchange membrane. So we went about preparing this membrane by starting with an unmodified cation exchange membrane. This was then immersed in an exchanging solution of manganese chloride so that all the functional groups present inside the ion exchange membrane would exchange the protons for the manganese. This membrane was then immersed in an oxidizing solution to convert the manganese inside the membrane, manganese ions inside the membrane into HMO to make our HMO-loaded membrane. So we can vary the amount of HMO present inside the membrane by changing the time that the membrane is immersed or equilibrated in the manganese chloride solution. So by varying those times, we made two different kinds of HMO loading membranes. One with a low loading of about 69 milligrams per gram of membrane. So this is when the membrane was immersed in the exchanging solution for about half an hour. And then we had another high loading membrane with about 170 milligrams of HMO per gram of membrane, where the membrane was immersed in the exchanging solution for about 24 hours. So when we characterize the membrane first with TEM, we clearly see, compared to an unmodified membrane, we see some nanoparticles present inside the HMO membrane. We then wanted to characterize the nanoparticles, and we started with XPS, and we found that we found specific manganese peaks for the HMO modified membrane. Further, the FDIR analysis showed us showed us stretching vibrations of hydroxide at about 3,400 wave number, and stretching and bending vibration bagging corresponding to the 600 to 700 wave number, essentially indicating to us that some form of manganese oxide or hydroxide has been incorporated into the membrane. So once we made the membrane, we next wanted to study the phosphate transport and possibly selectivity. And for this, we used a diffusion cell without applied potential. Where there was no applied potential, we were just looking at concentration gradient as the driving force for phosphate to cross the membrane, and also in the presence of an applied potential to see what the flux of phosphate through the membrane would be. So when we first characterize the concentration of phosphate in the receiving solution, where the slope of this line would give us the flux of phosphate through the membrane, we see that for unmodified CEM, except the first hour, we see a pretty flat line, a plateau, and we expect. And that is explained by the cation exchange membrane being extremely selective towards cations and preventing anion transport. When we then use a high loading membrane and do not look at the phosphate flux under no applied potential by just using a concentration gradient, we see a slow but steady flux that slowly increases over the duration of the experiment. When we use the same membrane and apply a potential across the membrane to facilitate higher fluxes, we see the flux transport of flux of phosphate really high during the first 3 hours, and then a slight plateau where the flux rate of change of concentration decreases. This decrease can be explained by the extremely high flux of about 2 volts being applied across the membrane, which leads to the generation of protons in the anode, which would then lead to change of speciation of phosphate to phosphoric acid, which would not be affected by the diffusion by the applied electric potential anymore, and would be only moving across by the diffusion by diffusion. So when we look at the low loading HMO, we see that the flux is constant and slowly increasing. However, this highlights the importance of HMO loading, where a much higher loading gives us, where twice the loading will give us a much higher flux compared to a low loading membrane. When we look at the separation factors of this membrane, this was done in a mixed ion solution. So the feed solution consisted of 1 millimolar of sodium chloride, sodium sulfate, sodium nitrate, and sodium phosphate. And the permeate solution was DI water. We had applied a cell potential of about 2 volts. And we see that our membrane provides superior phosphate selectivity over all other ions present in solution. Most importantly, it allows for selective transport of a bulky ion such as phosphate over much smaller ions in solution. And for all of these ions, ion pairs, the separation factors reported were in double digits, which had not been reported previously. And this was the first study that was giving us such high separation factors. So having demonstrated having developed a membrane that can effectively transport phosphate across, we wanted to study the ion transport dynamics. Is it actually happening through the outer sphere complexation that we hypothesized? So for that, we used molecular dynamic simulations. And what they showed us was that the negatively charged polymeric matrix of the ion exchange backbone disrupted the weak electrical double layer of the HMO, of the hydrous manganese oxide. This caused the sodium ions to be pulled away from the HMO vicinity and the phosphate ions to be pushed away from the polymer. Most importantly, they showed us that phosphate ions form outer sphere complexes with the HMO, where it follows a diffusion pathway that looks something like this under an applied concentration or potential gradient. Okay. So it showed us that the presence of HMO particle increases the mobility of phosphate by about 20%, and the sodium mobility dropped by 8%. So this was for a modified HMO membrane, and compared to that of an unmodified membrane, the mobility of phosphate increased and sodium dropped. The presence of an electric field accelerated the ionic mobility by about 21% for phosphate. And finally, the phosphate mobility in the HMO CEM was much higher compared to the pure CEM. And it also showed us that the ions can hop across adsorption sites on and between adjacent HMO particles along a driving force gradient, which could be concentration or applied potential. So finally, the last thing we wanted to study was the ion performance metrics. And we wanted to improve ion transport. What we observed in our flux studies was that although the flux of phosphate, the selectivity of the membrane towards phosphate was extremely high, almost up to 100, depending on the anion, the flux of phosphate through the membranes was low. It was almost 2 orders of magnitude lower than that through an anion exchange membrane. I do want to reiterate here that for an ion exchange membrane, the selectivity would be about 5, whereas for our membrane, we achieved a selectivity of about 100. However, in our studies, we also observed that increasing the amount of HMO within the membrane increases the flux of phosphate through it. So what we wanted to do was develop a model to predict the optimal HMO loading in membranes, which would allow us to give us much higher phosphate fluxes. So what we did was develop a mathematical model based on the microheterogeneous model for ion exchange membrane. And what this does is divides the ion exchange membrane into 2 phases: the gel phase, which is the polymer, and the intergel phase, which is essentially the pores present within the polymeric membrane. The model was used to predict the flux and transport number for phosphate and other anions, and then extrapolated to estimate the optimal HMO loading that would be needed to increase the phosphate transport across the membrane. So for that, we started with the Nernst-Planck equation. This is slightly modified, where the diffusion that I guess we are more familiar with in the Nernst-Planck equation was replaced by a conductance coefficient. So increasing the HMO loading of CEM affects its properties, including water uptake, ion exchange capacity, diffusion coefficient, and a few others. So extrapolating them is driven with uncertainty. So we tried to develop a model that can be as close to experimental predictions as possible. This inductance coefficient is dependent on the inductance coefficient of the gel phase, which is dependent on the fraction of the gel phase present in the membrane, and the intergel phase, and which is also dependent on the fraction of the intergel phase in the membrane. The alpha is a structural parameter, which is a fitting parameter. It varies between -1 to 1 and represents the connectivity between the intergel and the gel phases. So that was for an unmodified membrane. In the presence of a nanoparticle, such as the HMO, the equation for inductance coefficient modifies into this form, where F sin is now the fraction of the nanoparticle present inside the membrane, and L int is the inductance coefficient, is still the inductance coefficient of the intergel phase. Beta is an additional fitting parameter, very similar to alpha in terms of the structural parameter of the membrane, and it also varies between -1 and 1. So what we learned from this project was that our model estimated that we would need a loading 3 times what we currently have to increase the flux to about 38 millimoles per meter squared per hour, which would be almost 2 orders of magnitude than what we currently have. And I also would like to add a note that once I left the lab, my Professor Jasby's lab back at UCLA did work on increasing the loading of HMO and were able to achieve really high phosphate fluxes through the membrane with a high enough loading. So overall, with this project, we developed a highly selective membrane using outer sphere chemistry, which achieves separation factors of about 100 in mixed salt solutions. And was selective for a bulky ion over much smaller ions in solution. And more importantly, we learned that we can improve ion flux with increased loading of HMO, which has been demonstrated in a recent paper that came out of Professor Jasby's lab. So with that, I'd like to thank my advisor, Professor Menachem El-Melik. He's my postdoctoral advisor, initially at Yale and now at Rice. my advisor, Professor David Jaspi at UCLA. My collaborators, Dr. Piotr Zarzicki, who worked on the molecular dynamic simulations at Lawrence Berkeley, and my funding agency, USDA. And of course, my labs during my tenure in Professor David Jaspi's lab, and now in Professor Elimelik's group. So with that, I'll be happy to take any questions. Thank you.
Okay, thank you very much, Peter. So as I mentioned, we will hold the questions to the ends after the two presentations. So for now, if you have any questions, if you don't want to forget, you can also post it in the Q&A using the Q&A function, and then we will come back to these questions after that. So with that, let's continue with the second presentation from Dr. Yiming Liu, and then the topic is mitigating calcium carbonate nucleation and growth through continuous ion displacement via alternating electric fields. Yiming, please go ahead.
Yeah, thanks, Dr. Xie, for your kind introduction. Hi, everyone. Welcome to my talk. And thanks for the IWA Nano and Water Specialist Group for having me. My name is Yiming Liu. I'm currently a postdoctoral fellow at Rice University, focused on water treatment technology. My presentation today is about using electrochemical methods, more specifically, alternating electric fields to create continuous ion displacement for the prevention of calcite precipitation. The overarching goal of my research in general is to facilitate the circularity of water and critical minerals. Specifically, I developed platform treatment processes by explore a union of membranes, electrochemistry, and advanced materials, all these different areas with one single focus, solid water interface. Now, the interfaces come in all shapes and sizes. For example, you will have interfaces associated with ultra-porous materials, heat exchangers, and polymer membranes for all these different applications. Today, we are focusing on leveraging the electro-water interface for mineral scale prevention, as you can see here. Mineral scales are layers of mineral crystals built up on the surfaces of heat exchangers, pipes, and membranes, as shown here. These buildups can create serious challenges, such as reduced heat transfer and low water flows. Using the example of calcite here, the root cause, using the example of calcite here, the root cause for the scaling is the microscopic level collision of mineral ions in the supersaturated solutions. This results in nucleation followed by the subsequent crystal growth. This process can occur either in bulk solution as homogeneous nucleation and on the surface as surface-induced heterogeneous nucleation. Several approaches has been adopted to prevent mineral scale formation. They are electrochemical processes, chemical addition, and surface modification. The unique advantage of electrochemical approach is that one is chemical-free. It is much less chemically intensive than using anti-scaling. Plus, it is very simple to operate compared to the complex surface chemistry involved with the surface modification. By varying the potential on the surface, you can easily attract or repel the mineral ions. As shown in the figure here, there is a very big, thick layer of sulfate ions that push the nucleation zone into the bulk solution, successfully reducing the surface scaling. Alternating potential has been demonstrated in several reports to mitigate the mineral scaling during membrane filtration, where you have a conductive nanotubes on the membrane surface. As you can see in the figure here, the water flux, where you apply an AC, is much more stable where you don't have any potential apply. And also, it is slightly higher where you have where you apply DC potential. In addition, the mineral scale coverage on the membrane surface is much less under the AC conditions. However, the mechanism behind this these phenomena was not very well understood. It was believed that this phenomena was related to the ion transport impacted by AC potential through the electrowater interface. My hypothesis for this project is that alternating potential can drive the continuous displacement of ions in the entire solution and also on the surface, which overwhelms the ion collision, thereby eliminating both homogeneous and heterogeneous nucleation and crystal growth. As you can see in the left figure here, where there is no electric field applied, the crystals are formed based on the collisions originated from Brownian motion. In contrast, the right figure here under alternating electric fields, you will continuously have the displacement of ions, which dominates the entire period, overwhelms the ion collisions, and thereby mitigating the nucleation. The ion transport at AC potential can be well described by the periodic charging and discharging of electrical double layer. As you can see in the figure, the negatively charged surface attracts a very condensed layer of positively charged and a very loose layer of ions. These unique structure is called electrical double layer, which in abbreviation EDL. Basically, you will have cations and anions separated to charge the EDL during this process. When you flip your polarity of your electrode surface, as demonstrated in this figure, from negatively charged to positive charge, you will attract a completely different set of ions, which are anions, and you will disrupt and form a new EDL. During this process, there are two time scales are very important. One is EDL charging time, and the other one is AC half period. Based on this equation, EDL charging time is a function of electrochemistry, and the AC half period is basically an inverse of frequency, where you can actually manipulate. The experimental setup here is relatively straightforward. Two titanium plate electrodes were immersed in the supersaturated solution for calcium carbonate, containing both calcium chloride, sodium carbonate, and sodium hydroxide. The test would perform under different electrical conditions, including AC potential, DC potential. Specifically, we measure current to characterize ion transport, ability for bulk precipitation, and coverage of mineral crystals for surface precipitation. An equivalent random circuit was developed to simulate the electrochemical system here. And this allows us to also calculate the current. The component for this circuit is that the UAC is the potential that we apply. REX is the external resistance comes with the power supply. RS is the solution resistance associated with ionic strength, and CD, which is the capacitance associated with EDL. As you can see in this equation, the current representing the ion movement is related to TAC, AC half period, and also the EDL charging. Consistent with what we described before. We further calculated the displacement velocity and the displacement length. The displacement velocity is directly proportional to the current. So you can confidently say that by varying either EDL charging timescale or the AC frequency, you will have different ion displacement. For the specific calculation of charging time, it is a strong function of EDL capacitance, and EDL capacitance as shown here, CD. And the EDL capacitance here is a strong function of ionic strength lambda D, as shown in the equation, and also a strong function of AC potential that you apply as well, according to the modified Poisson-Boltzmann equation. The figure here shows a characteristic exponential curve back and forth that represented the capacitive charging current. This represents the EDL charging and discharging mechanism that we observe in our systems. This charging and discharging can be well controlled based on the equation by varying your voltage and frequency to directly control the microscopic displacement velocity of the ions. Here are the results for bulk precipitation. Ignore the equation for L here. We will come to it when I bring it up. So during the initial 2 hours, without any applied potential, you will see an increase in turbidity. And as you apply a DC potential, which basically means a zero frequency, you'll have a very small current that shows a very slow displacement of ions. So you can see a limited reduction in turbidity. As we increase our frequency from 2 volts to 4 volts peak to peak 1 hertz, basically means positive 2 volts and negative 2 volts here, you will see a significant reduction in the initial 2 hours in terms of stability. As we continue the experiments by releasing, by stop applying potential for the following 2 hours, and we saw the turbidity increase resume. This suggested that we actually mitigated the precipitation instead of the precipitation happening elsewhere. As we further increase the frequency to 10 hertz, you can also see an increase of displacement velocity represented by the current. We achieved successfully a reduction in turbidity. However, as we further increase it to 100 hertz, the turbidity reduction, which means that precipitation prevention is relatively limited. This is where the L's comes in. The L here, as you can see, is a strong function of AC half period. At 100 hertz, the AC half period is very low. So you will have although you will have a very high displacement velocity, but the displacement length is very low. That limits your the prevention effect. Therefore, instead of frequency, we increase the voltage to try to mitigate the precipitation. As we can see here, the impact was not as significant as frequency, but we still achieve moderate mitigation in terms of precipitation. We further characterized the surface precipitation on the electrodes. It is also responsive to the ion displacement velocity and displacement length as the same way we observed in bulk precipitation. Furthermore, here you have SEM micrographs for both conditions and EVS mapping results for both conditions. At 0 volts, you have the coverage of calcium carbonate, and at AC potential, you'll basically saw no precipitation, consistent with the surface precipitation data that we collected before. Fast forward to the model. We calculated the ion displacement values and displacement length as a function of AC frequency. And we found a trade-off between displacement velocity and displacement length. At a lower frequency, you will have a low displacement velocity, as we've seen in the current turbidity data. And at a higher frequency, although you have a high displacement velocity, but you will have a very low displacement length that limits the effect of preventing the precipitation. You can only have this effect very well where you have a very high displacement velocity and a high displacement length around the frequency associated with EDL charging. And the model also tells us by increasing the applied voltage, you will have an increase in both displacement velocity and displacement length. However, the orders of magnitudes of increase is not cannot be compared to the frequency. The frequency was on the log scale, and this one was just on the traditional linear scale. That was also consistent with our experimental data. In a more quantitatively way, we summarized the impact of displacement velocity and displacement length using an overall displacement coefficient here. And we built a good correlation between our experimental measured stability with displacement coefficient. And we also back calculated the ion collision frequency from crystallization models. And we also have a relatively good correlation. This suggested that we, for the first time, built a direct connection from the prevention of precipitation all the way to the potential that we apply and the frequency that we have for the AC potential. Therefore, we can optimize the frequency and the potential that we apply to achieve a best prevention in terms of mineral precipitation. To summarize, we have 3 key takeaways here. The first one is periodic EDL formation and disruption at relatively high AC frequency induces rapid ion displacement that can overwhelm the Brownian motion of ions, which eventually led to the prevention of precipitation. The second takeaway is that the prevention of calcite precipitation is governed by the displacement velocity and the displacement length. Both metrics are very important. The last one is that the mineral scale prevention can fully prevent it by optimizing the frequency and the voltage of AC potential, but maximize displacement velocity and displacement length values. If you're interested, you're welcome to check out the recent publication in Nature Communication related to this project, and you can scan the QR code. If you're interested in more details, you're also very welcome to reach out to me if you have any questions, comments, or interest. With that, I would like to acknowledge my postdoc advisor, Dr. Shilin Lee, as well as my PhD advisor, Professor David Jasty and Eric Hook, and all my colleagues from current and the past, including APITA. And the funding agencies for this project, U.S. National Science Foundation Department of Energy and California Department of Water Resources. Thank you, and that's all I had.
Okay, thank you very much for the brief presentation. Now the floor is open for questions. So let's see. We have one question coming from the Q&A box. So did you look at the calcium precipitate crystal structure? Did it go from calcite to aragonite crystals? I think this is for Yimin.
Yeah, thanks for the questions. It's actually a great question. For our studies, we didn't capture the transition of crystal structures from. We only observed calcite on our in terms of our precipitation, but we learned from other studies that suggested once you apply an AC potential, you will have that sort of an intermediate structure of aragonite in combination with calcite. So that could suggest that is disrupting the early stage of the crystal formation. But yeah, I guess that's something published or impressed with other studies.
Thank you.
Mm.
So for some of the questions posed before, and then if the speaker already answered, that would be directly moved to the answered questions. I think the audience can also take a look if they're interested, but we'll try to cover the open questions. So there's currently no other open questions now. So let me ask a question to Dr. Liu as well. So I kind of interested in the kind of real-time formation of the basically the precipitates. Have you thought about putting your device under the microscope, and then you can still apply whatever electric field you want, and then you can really look at the system in real time, kind of under operando condition. Have you thought about it?
Yeah, that's definitely something that we thought about before. And setup that I could, I think that involves using some in situ, very advanced in pseudo X-ray characterization instruments. But for a very simple setup that we have thought about is to put it in the DLS, you know, the cuvettes in the DLS, and then we sort of attach a 2 copper tape, and that goes out from the cuvettes, and we apply the potential to the supersaturated calcite solution to observe that. That's something that we definitely thought about, but for the time purpose of that project, we didn't get a chance to do it. But I would envision that in that setup, you can have a better characterization in terms of the crystal size and possibly the numbers of the crystals that give you more information how this AC potential disrupt the formation of crystal.
I think they will probably provide a better, at least more data, more results for more like the kinetics of the process.
Yeah, that's for sure.
Yeah, thank you. And I have another question. Let me see. Yeah, there's another question I have for Dr. Adia. So when you synthesize a membrane, you try different loading of HMO. You have a low loading and a high loading, Have you tried to, I don't know, probably look at a cross-section image of the membrane to see, I think from your model you can see dramatic difference, but from the more like a image-wise, whether you will be able to see dramatic difference, whether, for example, when the low loading actually there's still not like significant pass, right? So if the loading is low, maybe they only reach the certain depths, but when you have a much higher loading, you pretty much penetrate the whole, that.
Unfortunately, that part of the study was limited because of COVID. So because that was right around the COVID pandemic. So, and we tried SEM which I was trained on. So we didn't see anything in the SEM. So then we had to move to TEM, which I was not trained on. So I was limited by the working hours of the personnel in the thing. So I could only go with one membrane, and I went ahead with the high loading membrane to see what the loading was. So, but that's a great avenue that I would also like to study further.
So I guess it will be very challenging to look at a cross section of the
Yes,
membrane, right?
DEM,
Most of
yeah.
people show, yeah. So if you very thin layer of the membrane, and then
Mhm.
okay, yeah, very very interesting work.
Yeah.
Do we have other questions from the audience? If you can also unmute yourself, I believe, and then ask directly to the panelists, to our speakers. So far, we don't see any questions in the Q&A box. Okay, so we have one more question from Apita. If you can see it directly.
So yes, so they were mostly done at lab scale, and unfortunately, one of the things we noticed was that the flux of phosphate was almost 2 orders of magnitude lower than that through an anion exchange membrane. So we didn't go ahead and test them with real streams. However, the lab that I graduated from continued working on this project, and they recently made a membrane with a much higher loading, which is giving them a much higher flux. So I believe that would be the next avenue of study where they tested on real solutions, real streams, and see what if the phosphate selectivity is still maintained. And so for the commercial application of such membranes, I believe would eventually depend on the selectivity in real world solutions, because pH is a huge factor that affects phosphate speciation itself and its transport across. So those are things that we need to study more at a TRL 5 or 6 level before we think about commercial application.
Okay. I actually have another question for you. So when you synthesize the membrane, so you start with a cation exchange membrane first, and then you modify it, right? So I think I understand a little bit about why you have a cation exchange membrane. So like basically the contact ions can still go
Yes, go
through.
through.
You can selectively only pass or only choose the
Mhm.
phosphate for the selectivity. But in the industry, for the battery, I think the HMO is it also kind of a battery material? I don't know, but I think that in the
It was,
battery
yeah.
side, they synthesize the kind of thin composite electrodes, right? We mix the certain active material with PTFE and then probably other additives. They make a thin film. And then basically my question is that because cation exchange membrane is already kind of expensive, right? So you're modifying that. I don't know whether if you can sacrifice basically my question is whether cation exchange membrane is necessary. Is it possible to form the similar composite membrane without using the cation exchange
Yeah.
membrane?
So the way we made these membranes was leveraging the chemistry, which is by exchanging the protons inside the membrane, H plus ions inside the membrane with manganese, and then oxidizing them in situ. However, the next study that came out of Professor Jasby's lab works on using HMO nanoparticles that are made outside and then embedding them inside a membrane. So although they still used a cation exchange membrane resin, then cast the membrane out. However, if you do not want to use a cation exchange membrane, if you want to use a regular polymer like PTFE, you should still be able to cast a membrane with that.
Okay.
But I can't guarantee the selectivity at that point.
Right. I guess in that case, if you don't have the blocking mechanism, the selectivity will
Yes.
probably get sacrificed. Yeah. Okay. Cool. There's another question for Dr. Liu. Have you applied your experimental setup to real waters, like hot water with high calcium magnesium concentrations?
Yeah, thanks for the question. At this stage, we haven't actually tested, but definitely that's a very good next step. That will be a logical next step for this project. I would envision that this technique, the scope for this technology is limited to the waters that without a really high level of TDS around the surface water level that should be suitable. And yeah, uh, uh, we haven't tested in short, but we believe it's a universal mechanism, and definitely there's some interesting to explore when you use this technology for this kind of blue waters.
So Dr. Lee, is that your setup, if I remember correctly, you use already a supersaturated calcium solution, right?
Yes, for the calcium solution, we are super saturated, but I think that it also she also mentioned the magnesium.
Right.
So yeah, I feel like it was sort of in a real wastewater that contained both species. So in theory, that should be uh, very much of a difference because it is taking advantage of the charges of the ions, where magnesium you also have double charges. So
Okay. Yeah, thank you. Okay, do we have more questions for our speakers? So currently we don't have any open questions. We still have some time. Okay, so we have one question coming for Dr. Liu. Do you think real water pH interferes in the setup?
yeah, yes, I do. I do believe actually I think it depends on the water chemistry. And so for calcium carbonate, precipitation is highly depending on the pH, as you might aware. Because if you have a relatively low pH, you will have limited concentration in the form of carbonate. They will exist in the form of bicarbonate. So your precipitation will be much less. And that's the impact of pH that I can think of for the calcium carbonate system. And if we extend it to calcium sulfate or other precipitation barium sulfate, they are not very sensitive to the pH. I At this stage, I would not think it will for this technology. I don't think it will have a real big impact from the pH. Unless it is relevant, unless it is affecting the anions or cations concentrations. Mm. And also, I do have one data that characterizing the pH in the solution for this studies. It shows a continuous diffusion of CO2 in the alkaline solution. The pH is dropping, but um, we measure the pHs under all the electrical conditions. They are all very consistent, and it doesn't seem to impact our prevention of precipitation, even though in a calcium carbonate situation. And we also run long-term experiments for 24 hours. That's in the supporting information of that paper. and we at 4 volts peak to peak 1 hertz, we still achieve near 100% prevention of precipitation, even though the pH is kept changing from 12 eventually to 9 to 10. But yeah, that's the case for calcite. And again, I don't think that would be the case for calcium sulfate or barium sulfate.
Okay. So there's I think it's a separate question. You mentioned calcium sulfate a little bit, but under the concept pH. But there's a separate question about calcium sulfate. I think it's general about whether the AC can also control the precipitation of calcium sulfate scaling.
Yeah, I think it's an interesting point. The previous studies, also in Professor Jasky's lab, is our previous published work to use electroactive membranes to prevent the scaling by applying AC potential to it. In that studies, I think calcium sulfate was tested, and it also shows an impact in terms of preventing the precipitation. And if I could envision it a little bit more, the calcium sulfate tends to have higher concentration for its supersaturation, and it will necessarily have a higher frequency to induce a higher displacement velocity. But it all depends on the experimental setup. I think you can have a precise calculation. If you look at the paper, there is a model proposed that that considers the factor of ion composition. So you can basically plug the ion composition of calcium sulfate in there and have an estimate of the ion displacement velocity and converted it to the potential performance of precipitation prevention. So that would be some possible solution and possible scenarios that I can think of for now.
Okay. So, Amy, I have another question for you. Is that I think there's a commercially available product for like individual households to control. Like they mentioned that you can use it to without using any chemicals, but it's like kind of some device using also similar like a alternating electric field, something like that, to directly kind of install. Kind of they have some wire wrapping around the pipes, and then they mention that this can significantly kind of mitigating the water precipitation due to the harness. So have you seen that, and then do you think that's a kind of similar mechanisms as you studied in your study?
Yeah, thanks for the question. Yeah, I think this one is interesting. So when you apply an electric field to mitigate mineral scaling, there are definitely different mechanisms. For our mechanism, I think it's different than the mechanism for the commercial product. I think they are a big chunk of the work that was focusing on using electromagnetic fields for the mineral scale prevention. That mechanism was, I think that they are impacting the actual dipole interaction, if I understand it correctly. It is essentially a different mechanism than what we propose here. What we propose is the sort of ion dynamics, electrokinetics mechanism, while they involve a wider consideration of magnetic field and the affecting the exact ion properties for the mineral crystal formation.
Okay. Okay, thank you very much. Let's see. I don't see any more questions coming out, and then I think we are also about the time. Okay, so with that, I would like to conclude the Q&A part. So thank you very much for both of you for the great presentation. And then I think we have one or two final slides to show. Go back to the wait. Yes, okay. Yeah, so basically there's upcoming IWA webinar events, and then so this is a Water and Development Congress and exhibition, which will happen on December 8th to 12th in Thailand. So if you're interested, I think the conference still I think the abstract submission is already closed, but I think it's still you can still register conference and try to attend the conference if you're interested. So next slide, I think just a final reminder that if you're interested, if you're still not an IWA member, welcome to join us. And then you can, by attending this webinar, you have the privilege to see the code. And then as a new member, you will get 20% discount for the membership. Okay, with that, thank you very much for joining today's webinar. And thank you all. Have a good rest of the day. Thank you very much.
Thank you. Thank you.